Right. So let's get started. My quick reminder, we are going to have a lecture instead of a discussion section tomorrow. Because of travel schedule next week, I'm making a small adjustment. Just go to the same room as the discussions and don't come here. Okay? Go there and just come there, we'll have lecture there. Next Tuesday, I will not have the lecture, but that will be substituted by the discussion section. Tuesday, come here as usual. The TA will come here and hold the discussion. Okay, so just go where you usually go. You just swap the discussion and the lecture for the next couple of class meetings. Okay, so let's continue from where we left last time. So this is just a recap of what we did in the first 2 or 3 classes. It shows the picture starting from hardware abstractions. These are the hardware components you find on a typical machine. There are OS services that are provided by the operating system that use those hardware abstractions. And I added a new column here which shows you what are the user abstractions. What do users actually see for each of those OS services and that piece of hardware. So for a processor, you see this notion of a process. For memory, you see this abstraction of an address space within a process. For I/O devices, you actually see the I/O devices, whether they're keyboard, mice, touch screens, and so on. As far as storage disks are concerned, you see files, directories, and so on. And where networking and distributed systems are concerned, you see networked applications like file system, mail clients, browsers, and things like that. So that's a high-level recap of the last 2 or 3 classes. Last time we talked about system calls. If you remember, I mentioned a little bit about how system call work at OS level. Basically how the operating system implements it using a vector. There's a number associated with each system call. You have a table. Whenever the system call is invoked, you index into that table. The table points to the location in the kernel where the source code, not the source code, but where the binary code for the system call resides, and that's where you go and execute the system call. Okay. And then I talked a little bit about the structure of operating systems. We talked about monolithic, modular, microkernel architectures, and the layered approach. Okay. So with that recap, towards the end of the class, we were talking about process management, and I'm going to continue that discussion today and for the next couple of classes. I defined this notion of a process. A process is a program in execution. A program is simply code that you write or code that the compiler has generated. It's stored in a file on disk. When you execute that program, you get a process. Okay? There could be multiple instances of a program executing. Each is its own distinct process. Okay? We talked a little bit about how processes work, and I mentioned this notion of a process execution state, which is basically what state the process is in, whether it's new, ready, running, terminated, and waiting. Okay? And then you cycle between the states until the process finishes. So that's a quick recap. I'm going to actually start with a small story, which I like to tell occasionally in class. These are called parables in computing. This story has nothing to do with computer science, but we try to learn some CS or some technical moral lesson from the story. So this is going to be a parable on 3 intelligent men, could be women, let's back up men for this particular story, and the food. Okay, so there are 4 friends that grow up together. They're good friends, and when they grow up, they decide to go off to a city to find some jobs, and the path to the city leads them through a forest. Okay, so they're walking through the forest, and they come across some bones. Okay, so the first smart guy says, "These look like bones of a tiger, and I'm going to prove it to you. I'm going to assemble it together and show that it's a skeleton of a tiger." And he then assembles it, and sure enough, it's a skeleton of a tiger. Okay. And then the second guy says, "I can do better than that. I am going to actually skin this beast and actually prove to you that it is a tiger. You can actually see that it looks like a tiger." And then he puts some skin on this skeleton, and sure enough, it looks like a tiger. Okay? And then the third guy says, I can do even better. I'm going to breathe life into this animal and prove to you that it actually was a tiger before it died. Okay, and then the fourth guy who is in this story, the fool, says, are you sure you're doing the right thing? Is it smart to actually breathe life into an animal that can do harm? And then these three guys brush him aside, saying, don't bother us, we are trying to prove whether this is really a tiger. So then the third guy goes and breathes life into the animal. The tiger comes to life and eats up the three guys. And the fool has actually, in the meantime, run away and climbed the tree. So he's only okay. So that's the story. Now you can say, what does this have to do with computing? It doesn't have anything to do with computing, but all it's saying is there is always more to learn in life. You never know. You don't think that you know everything that you think you'll know. Okay. All right. So with that, we will continue the lecture. We'll occasionally do this once in a while, whenever I get bored. Okay. All right. So processes. We defined what a process is. I talked about what a process looks like in memory. It has code segment, heap segment, stack segment, and so on. And I talked about process execution states. So we are going to continue the discussion from that point on. Okay. So we will look at a key data structure called the process control block of the PCB. Okay. So this is an important data structure that the kernel is going to maintain. Okay. What it is there is this data structure tracks everything that the kernel needs to know about the process that's currently active. For every process that is running, meaning that's active in the system, there is going to be an entry in the process control block. And it will store all of the information that the OS needs to know. And this is a list, not an exhaustive one, but this is a representative list of all the fields of an entry in the PCB. Okay, so you will track the process state. You meaning the OS is going to track the process state, saying is the process running, waiting, ready, so on. Okay. Processes have ID, so you'll track the process ID. You will actually keep all of the registers in the process control block. You will save them whenever the process is not running. So there has to be storage space for all of the registers, program counter, stack pointer, general purpose registers, and so on. Okay, so you have those entries in the PCB. You will have memory management information. At this point, I'm not going to define what that is, but when we come back to memory management, we'll see that you store page tables and base registers, limit registers, segment registers, and so on in that memory management information. So this allows the kernel to determine where in memory the process resides. Okay? Because it needs to track what space has been allocated, how much RAM has been allocated to each process, where does it reside, where does each process reside in memory. Okay, so all of that is tracked by the kernel, and that information is stored in the process control block as well. You have other information like the owner of the process, what files are currently open by the process. There will be queues for state queues, and there will be pointers to state queues. I'll show you a picture in a slide or two. A scheduling information which tells the kernel what is the priority of the process, what is the priority level should it be scheduled at, and so on. Okay? And IO status, the process is doing IO. You can track what IOs are in progress and whether they're finished, are they still in progress, and so on. Okay, so all of this information is going to be stored in the PCB. Whenever a process starts, an entry is allocated and all of the information about the process is stored. Yes, question.
So there's just one PCB?
Okay. Is there one PCB? So think of PCB as a data structure. Okay? You could implement it as a linked list, you could implement it as an array, you could implement it as any data structure you want. Within that data structure, there's an entry for each process. Okay? So the PCB is the list of all of those entries. List, linked list, array of all of those entries. Okay? Any other questions? Yes.
How does Unix implement PCB?
How does Unix implement PCB? What data structure it uses? Is that the question? So typically you can use a doubly linked list as the most effective data structure. If you have arrays and things like that, then the array is statically allocated. That limits the number of processes you might have in the system. If your linked list, you can always allocate a new entry and put it into the link. So linked list is a common data structure that used to implement the PCB, in particular a doubly linked list. Okay. But then that is left to the OS designers. Unix is not one thing, as you know. There are many flavors of it. There are many versions of each flavor and so on. So it hasn't stayed that way for since the bit began. But doubly linked list is a good way to think about it. Okay, so PCB is a key data structure that you have to keep in mind. And I'll now describe this notion of a process queue state. Okay, so as I mentioned last time, each process could be in one of 5 states: new, ready, running, waiting, terminated. Okay? The way you actually track what state a process is in is, for each state you keep the list of all the processes that are in that state. So if you are in IO state, then your PCB entry will be in an IO list. If you are in the ready state, there will be a ready queue or a ready list that has all the entries of processes that are waiting for a turn to execute on the CPU and so on. So for each of those states that I showed you, okay, so these are the state. For each of those states, think of it as that you have a list, and that list contains all the processes that are in that state at that instant in time. Okay? That allows the OS to also track what processes are in what state at any given point in time. Okay? So here is an example of what I just showed you. So what is shown there is at the top is a ready queue. Okay? So each entry here, so this entry, okay, is a process. Okay? So it says PCB for process X, that's the entry for X, the process control block entry for process L and A and so on and so forth. Okay? So each of those rectangles is a process, and you will see that here you have a doubly linked list. Okay? So that allows you to traverse the list and take entries out from a ready queue, move them to the wait queue, run queue, and so on and so forth. Okay? So if the OS needs to figure out what processes are ready to run, okay, and which one gets to go next, it just has to examine the ready queue in this case. Okay? Because anything in the wait queue, by definition, is waiting for IO to finish or waiting for some event to occur. So those processes are not ready to run. Okay? If you are in the new queue, you are not even ready. So you are just the process being set up and so on. So this is how the OS is going to track which processes are in what state at any given point in time. So you keep a doubly linked list of these entries. Yes, there's a question.
Is the wait queue connected to the ready and everything else? Because that picture, maybe it's just the picture where they're not connected. But
okay, the wait queue connected to the ready queue. So there will be something else that allows the OS to enter the head of the wait queue and the head of the ready queue and so on. So they will not be actually linked in the queue. There will be separate queues, but you will have the pointer to the head of the queue or the pointer to the tail of the queue that allows you to traverse it. Just as in any linked list, you need to have pointer to the head and the tail. The same would be true here. Okay. Another question? Yes.
So, I'm sorry, you want to address this, but PCBX, is that just one process?
Yes. So this is a process. Right? This is a process. These are all the fields I was talking about: the process ID, the owner, and so on. These are not processes. This whole thing is a process, and these are fields of the process control block.
Okay, thank you.
Okay, so that's an example. So now we learned about what's a PCB. We talked a little bit about process execution state. Let us start define another term called context switch. Okay? So context switch essentially is a set of steps that the kernel performs to switch from one process to another. Okay, so let's say process A is currently running on the CPU. Okay? And for some reason, let's say you want to switch to process B. A good reason to do that is process A wants to do IO. So it has to go to the wait queue. It's no longer able to run. So then you have to switch to a different process. We'll also see another reason to switch between processes is CPU scheduling. You're given time slots, and when your time slot expires, it's time for some other process to run. Okay? So there are a number of reasons why you have to switch from one process to another. But whenever you switch from one process to another, you perform what is called a context switch. Okay? Now this is a somewhat expensive operation because there are a number of bookkeeping items that the kernel has to perform in order to switch from one process to another. And most of these relate to saving the state of the currently running process into the process control block and restoring the state of the process that is going to run next from the PCB into various hardware registers and so on. Okay? So when you run, want to perform a context switch, you are going to suspend execution of the process that was running. The kernel will then run, and it will take all of the register values, which is the program counter, the stack pointer, all of the general purpose registers, and then store them into the PCB entry. If you go back a couple of slides, I showed you that the PCB has space to store the program counter and the stack pointer and so on. This is a memory data structure. So you are going to take the actual registers and store them there. Okay, you save them there, so that when you resume execution, you can reload the register and the process will start exactly from where it left off. Okay, so you are going to save all of these registers into the PCB. You are going to pick the next process to run. Typically, to do that, you have to run a CPU scheduling algorithm, which we have not encountered yet, but which we are going to see very soon. Okay? And then once you do that, you pick the next process, and then you are going to look at its PCB, take all of the register values and put them into the register. Okay? So doing this is going to incur some overhead. Okay? That's the overhead of context switching. While this is happening, nothing useful is happening in the system. No processes are running. Process A has been suspended, you are simply saving its state. Process B, which is supposed to run next, hasn't started running because you are loading its state from the PCB into registers. Okay. So this is not a cheap operation. So you have to ensure that whenever you perform a context switch, whatever runs next is going to run for a sufficiently long period of time for you to recoup the overhead of the context switch. So let's say context switch takes a few microseconds. Okay? You don't want the process that runs next to just run for a very short period of time and then give up the CPU. So in that case, you have to perform another context switch. That's more wasted overhead from efficiency standpoint. So the overhead of a context switch has to be amortized over the actual running of a process. In other words, the time for which processes actually run on the CPU must be much, much larger than the time you take to perform the context switch. Okay, so that overhead, typically you want to keep below 1%. Okay, meaning if it takes if you run for 99 cycles, then not 99 cycles, 99 time units, context switch should be 1 time unit in relation, okay, or lower. Otherwise, you are paying too much of a tax to perform context switches. Okay. Now, in most operating systems, you may either like Linux or Mac or Windows, you may do hundreds or thousands of context switches every second. Okay. So what that means is typically the time slot for which you run maybe 1 or 10 milliseconds, and so you may do tens or hundreds of these, okay, sometimes thousands of these every second. So you want to keep the context switch overhead as small as possible in relation to the time for which each process runs. Okay. We will come back to the overhead of context switches when we do CPU scheduling, okay, just so that you can understand what is the typical length of a time slot, what's the time for which you do a context switch and so on. Okay, for now, all you need to understand is what is a context switch. Context switch is the set of steps we perform to switch from one process to another. It involves saving the state of a process into the PCB, loading the state of the process that's going to run next from the PCB into register. Okay, so those operations are all part of a context switch. Okay. So now with that background, we know what's the process control block. Okay, here's a question there, yes.
So with the PCB, it's like a double linked list, and each like node or whatever in the linked list is like a stack queue for a process, right? Yes. Okay.
Yeah. PCB is a doubly linked list, and there's an entry queue or a stack, any way you choose to implement it for each process. Okay, so now we'll talk a little bit about creating processes. Okay, your question there, yes.
You said all the registers are backed up in the process control block. So we have limited number of registers in that case. So if there are two processes which are interrupted, in that case, both of them have a state which will be shared between the register will be shared between them, or they'll go in the memory.
So you are asking a question: if there are two processes that are interrupted, are they sharing registers, and where do they go? Okay, so for now we have assumed a uniprocessor single core system. Remember I said in the first lecture that by default, whenever we have this discussion, we'll assume there's only one core. There's only one core, one process can run. If one process is running, all the registers are its registers. There's nothing else that are using registers. If you have multi-core system, everything here has to be generalized. You have to take the registers and decide which registers go to each core. Typically, cores may have their own registers dedicated to them and so on. Here we are not looking at multi-processor scheduling. That's some material for a graduate level. We are only talking about uniprocessor scheduling. So there are no complications. Okay, all the registers belong to that process. So whenever you do a switch, you just save all of those registers because they all by default belong to that process. Okay, so always uniprocessor system, no complications when you do context switches. Okay. All right. So now we'll talk a little bit about creating processes. Okay, so you basically here we'll try to understand what happens when you try to execute a new program. Okay, how does that become a process? How does all of that work? So now first thing that we will have to understand is how processes are created. Okay. Typically, a process can be created by another process. They don't just appear out of thin air. Okay. A process has to be created by some other active process in the system. Okay. So what that means is processes have what is referred to as a parent-child relationship. Okay. Every process has a parent process. That's the process that created the process. A process may have multiple children processes. If you create 3 processes, you will have 3 children. Okay. But every process has a unique parent. That's the process that spawned that process. Okay. So if you look at all the active processes in the system, you will actually see a tree structure where each node represents a process. All the children of the process of that node are the child processes of that process. Okay, and I'm going to show you an example in just a second. So now, how does a process create another process or a child process? You use a system call to do this. There's a special system called in Unix called the fork system call. Fork is what is used to create a child process. So if a process wants to start a new process, another process, you call fork. That's going to create a child process for you. And the system will associate that child process to this process that invoked fork. That will be the parent process. Question then.
So when we turn on a system, I just turned on the system. The first process that should be spawned should be either the terminal or well basically the terminal.
Yeah.
My question is that when your machine is taken from rest to a start state, are the registers purged? If not, are they purged when you turn off the machine? Because if the PCBs are storing the register data, then when is the purging of the registers happening?
Okay. So you are asking 2 slightly related but also somewhat independent questions. So you are asking something about what happens when the machine starts up. Okay. So when the machine starts up, you run a boot process typically or a boot loader that starts up the kernel. Okay. So the kernel is basically the first process in the system, and then all these processes are in Unix is called the init process. All processes derive themselves from this process. Okay. So that's how your system is going to work. Okay. The second question you asked is what's happening to the registers. Right? So when you do a context switch, typically you will save the state of a registers into the PCB, and you load the state of new registers. When you load the new state of the new registers, the old register values are overwritten. So there is no such thing as purging happening, because what happens is you take what is in the registers, those values that they are all integer registers, you put them into PCB. You should pick another process and you see what register values are saved in the PCB. You simply load them. When you load them, the old values get overwritten. Okay? So they're automatically taken off.
So basically, when I turn off a system, whatever were the last processes that were running, the PCB values are still saved when I turn it on.
Okay, now I get the question. So you are asking what happens when you shut down the machine, right? So everything that you see here resides in RAM. Processes reside in RAM. Okay? When you shut the machine down, RAM is a volatile device. It is not persistent. Power goes off, everything in RAM is gone. Okay? Processes are actually not saved across boot cycles. If you reboot your machine, okay, all the old processes are gone. So you will not get them back because they are all stored in memory. So there's no question of register, let alone all the memory state is also gone. Okay? Because everything is volatile. Only what is on disk is persistent. Okay? Now your operating system may be smart enough to restart the application when you reboot a machine. Okay? But those are new processes. They are basically running the same application, but they are not the same processes that existed when your machine was shut down. So you have to keep this in mind. So when you reboot, nothing is coming back to you, everything is lost. And you can restart the application, but that's a new process. Any other questions here? Okay. All right, so now processes are created by other processes. There's a parent-child relationship between processes, and the way a process is going to be created by a parent process is you call fork. Okay, that will create. That tells the OS set up a new process, and then you are the parent process if you can go. Okay, so I'm going to show you how fork works, but before I show you how fork works, I just want to illustrate this parent-child relationship somewhat. Okay, so if you have a Mac, you can actually go and start up Activity Monitor, which is going to show you all the processes. Okay. Now this by itself doesn't tell you who's the parent, who's the child, but if you go into view and say review all processes hierarchically, you will see the process hierarchy. Okay, so you will see that the very first process here, which is process 0, is called kernel task. That's the kernel. That's what booted up, that got process ID 0. Everything is derived from that process. So you will see that kernel task started a process called launchd. That's the launch daemon that's going to start up other processes, and so on. So you will see that this is nested. So you see basically there's a parent-child relationship between each process. Okay, so you will see if you look at this thing is moving faster than I can click. So if you look at Google Chrome, you will see. Okay, hold on. All right. So when I logged in, there is launchd that started up, and then these are all my processes. Okay, so they all have parent as launchd. That's what started up. When you log in, you are given a process that launches all other processes that you start up and so on. Okay? And then if you look at each of these processes, some of them are child processes. Google has a helper process that did start up, so there's the parent-child relationship between these processes. Okay, so that's one way to look at the parent-child relationship. If you go to the Ed Lab and log into Linux, you can actually run this command called pstree, okay, which stands for process tree, and it's going to show you the same parent-child relationship. You will see that there's an init process that is the root process in your process hierarchy in your system. Okay, that is ID 0. Everything is a child process of the root or a descendant of the root. Okay, of init rather. So then you will see the whole set of processes that started up as part of boot, and then you will actually, if you go through this carefully, you will see that. Okay, so when I logged in, SSH started up. SSH created a bash shell created pstree that I was just running. So you will see that hierarchy there between the processes that I created when I logged into the machine. Okay? So just to illustrate the process hierarchy on a system. Okay? You can see this. I don't know how to find this hierarchy on Windows, but there must be similar utility. So I showed you how to do this in Linux and on a Mac. Okay, so that's the process hierarchy. So now let's go back and look at how to create processes. Okay? So I'm going to tell you a little bit about how fork works. Okay? So when you call fork, okay, this is what it does. Okay? Fork tells the OS saying create a child process. Okay? And what the OS is simply going to do is it doesn't know what should be in the child process. Okay? So it is simply going to take the parent process and make a copy. The child is going to look like a mirror image of the process, of the parent process. Okay? So the child, so whenever you do a fork, the OS simply takes the parent process that invokes the fork and makes a duplicate process. Okay? So it basically takes all the memory contents, makes a copy, so the child looks exactly the same as the parent at this point in time. Okay? So the child process is a replica of the parent process. Two distinct processes, but they have the same code, they're identical in all respects. Okay? Now, then what happens is now the child is its own independent process, parent is its own independent process. They can execute and they can execute different things. But when fork is invoked, they are actually the identical copies of one another. And what fork is going to do is when it returns from its invocation, the return value is going to be actually different in the child and the parent. In the child process, fork is going to return 0. In the parent process, fork is going to return the process ID of the child that just started up, so that the parent knows what process was created and what is the ID of the child process. Okay? And if you use these return values to do interesting things, and I'm going to show you what that means. Okay, so here is an example piece of code that shows how you can start up a process and then create a child process from that process. A simple piece of code. There's more comments here than lines, and it looks a little busy, but I'm going to explain what's going on. So for our purposes, the only 3 lines that matter are this line here where we call fork and this if and else. Okay? So in this line, you're basically calling fork, which is a system call. Okay? So this is going to create a new process. A new process is going to have the same code as this process. It's going to basically be an identical image of the parent process. Okay? Now, both the child and the parent are at this point in execution because they are both identical copies. So each of them will now continue executing independently and they will go on to the next line. Okay, here's what's going to happen. In the child process, the OS will make the fork return 0 as the return value. Okay? And in the parent process, you are going to return the process ID. Okay? This is the only way the child and the parent can distinguish themselves from one another. So you take the return value, you say fork returned some value, you store it into this integer variable, and you say if the value returned was 0, you are the child process. So in this if, you are going to do whatever the child needs to do. Typically the child is going to execute a new program. Okay? Because there's no point creating identical copies of yourself and doing the same thing. You create a child so that the child can do something else. Okay, so you are going to have the child part of the code here, and then in the else part, which is if the value returned by 4 was not 0, you do whatever the parent is supposed to do. Okay? Here the parent is simply waiting for the child to finish, okay? But you can do whatever the parent needs to do. I guess there's a question.
So you say the child returns 0, but isn't every single process a child of another process? So like, does it return 0 to its parent process, but it can also return
the fork is going to return 0 in the child process. I'm going to draw a picture that will make this clear. Okay? In the parent, you will always get the process ID of the process that was just created. Okay?
When the child terminates, you get its ID in the parent.
Not when the child terminates, when the child starts up. Because when you start up, you will get that process is going to get its own ID. The parent will be told, this is the child that was created, here is its ID.
And so it returns 0 to itself?
It returns 0, the OS is going to return 0 in the child. Okay, and I'm going to draw a picture because this is important to understand. This is also going to be the first lab assignment to create some processes. Okay. So here is how it works. So let's say that code there is this process A. Okay, so here you are going to figure. So here we are going to call fork.
Why using a different color? That's what it's
Right, there's no good. Okay, this is better.
much better.
Okay, so this is process A. It's called fork. Okay. So what happens when fork executes is the OS is going to create another process, okay, which is the child process. Child process is going to be identical to the parent. Everything that is here will be in there as well. So all of this code is also going to be in there. Okay, so here we'll have the same thing. Both the parent and the child are at this point because they are copies of one another. Okay? So you created a child, it's basically the same as the parent as well. Not very useful still, but we'll see how to make it more useful. Okay, and then you say if I equal to 0, this is child. Okay, and then you say else So here also you are going to have the same code that you wrote. That's basically that code that's there. Okay. So here's what's going to happen. Okay. Fork created a child, that's that process. The OS is going to make fork behave differently in the child and the parent, in that the return values of fork will be different in the two processes. Okay. In the child process, the value that's returned by fork will be 0. The OS will make fork return 0 in the child because the OS knows what's the child. In the parent process, you will basically get the ID of the child. Let's say this process and ID, PID is 100. Okay. Here, fork is going to return 100. So I is going to get value 100. Here, fork is going to get value 0. Okay. This is the only way the parent and the child are different at this point. So now, based on the value, if you check the value, you can make the parent and the child do different things as they continue to execute from this point on. So in particular, we have written this if-else statement. We will say if I equal to 0, okay, then you are basically, so in the child this condition is true. Because fork returned 0, so I has 0. So the child condition is true. So the code for the child you put here. So the child is going to begin executing the if part of the process. In the parent, I is not 0. Okay? So this condition is not true in the parent. So the parent will start executing the else part. Is that clear? First of all, fork is going to return two different values in the child and the parent. So because you have an if statement that checks the return value of fork, the child will start executing the if part and the parent will start executing the else part. And we'll see what to put in each case.
Why is it a printf statement printing? Like I know there's a comment there, but I don't really understand.
What's the question?
The printf statement in the child.
This one?
Yeah, why doesn't that get printed?
We haven't come to that. Give me a second. Yes, I'm trying to understand what the if-else statement is. Yes.
What happens if the system is unable to create another process?
What happens if the system is unable to create another process? Fork is going to return an error value which is typically negative. Right? You should check for error conditions, which I have not. That's not a good programming style, but I'm ignoring errors just for the moment. Okay? Yes.
So when the parent of process A forked it, didn't that leave another fork call in A that would equal to 0?
Yes.
But so that code will look different than that.
So I'll tell you why. So the parent of A would have done the exact same thing. Okay, and then you'll see why A is now doing what it's doing. But just hold on for a second.
Wait, but also if you want to fork multiple processes.
Yes, I'll tell you how to fork, or you will fork multiple processes shortly. Let's try to do one fork first. Okay. So now what you need to understand is the child is in the if part, the parent is going to be executing the else part. Okay? So now let's try to do, now what do we do just based on this understanding. So now you typically don't fork and create exact copies. You want the child to do something else. Okay? So the way you are going to do something else is, you know that you are going to be in the if part. You are going to write some extra code here. In particular, you are going to call another system call called exec. Okay? Exec is short for execute. Okay? Within exec, you can give any name of any program in your system. So you can say, let's say /applications/pro here. Okay? So what that will do is, since the child is actually executing within the if part, it will execute the exec system call that will tell the OS the child wishes to execute Chrome. Okay? Then the OS is going to take Chrome. Okay? It will actually scrub this entire process, which looks like this at this point in time. Okay? When you call exec, it causes the OS to scrub the process and load Chrome into the process. Okay? So this will now cause the child to start executing Chrome, if that's the argument to the exec process. You can give whatever argument you want the child to execute. If you want to execute Safari, you would say that. If you want to execute Word, you're going to say Word. You can even take a command line input saying what program do you want to execute. User types a command, and that's the command you're going to give to the argument to the exec that will cause the OS to execute this process, to execute this program within this process. The way you do run exec is exec actually wipes the entire process clean, okay? Loads this new program into that process and starts executing that process. Okay? Is that clear? What's happening in the child? Yes, question.
Yeah, I was going to ask if exec was blocking or non-blocking, and I'm assuming that.
Exec is a system call that it's a blocking system call, and that you call exec was freezes the process, wipes its contents, loads whatever that file is from the disk, starts and resumes execution of that process, but then it's essentially now a new process. That's called code.
So if there were a line after that.
Yeah, that's basically why you say if there's a line after this should never execute after exec, because at this point this process is gone, it's wiped out. Only if there's an error here will you actually come to this line. Error is you gave a value of a program that doesn't exist and exec is going to fail, then you are going to come into the. There's a valid argument, this process is essentially the child process is going to get wiped, so you will never see anything after the exec.
I guess if you wanted a non-blocking system, you just use another fork call.
So I'll show you what to do for another code. Give us a second. This is a question.
Yeah, I was just wondering, are the arguments just like the name of the program you want to turn it into?
So the question is, what are the arguments? There are many flavors of exec. That one says exec LP, I just said exec. They are actually all variants of exec. They take slightly different argument, but they all take one common argument, which is a string. That's the name of the program you want to execute. But they take other arguments as well. The question is.
So if exec starts up a new process, so whatever was in the running queue, or whatever was running on the on our processor right now, what happens to that? Does it go to the wait queue? What happens?
So first of all, exec is not starting a new process. Okay? You have already started the new process with fork. Fork is the thing that starts a new process. Exec simply executes a new program within that process. Okay? That's important. You're not starting yet another process here. Okay? This says that just take this program and execute it within this process that's already been created. Okay? That's first thing. Okay? Important distinction between fork and exec. Exec doesn't start new processes. Exec is executes that program in the current process. Second point you are saying is what happens to all the other processes. They are still there. They may be in the ready queue, they may be in the run queue. Nothing has changed as far as the other processes are concerned. You have yet another process that's got added to the system.
So this new process that that was just created after exec goes into the new queue, or the.
Okay, so here you will, when you are doing exec, you are actually going to be new because you are reloading, let's say in this case, Chrome into this. So it's not yet ready to run. So whenever you call exec, you will be in the new state for a little while. Then you will go back to ready once you are done. Okay. Some more hands somewhere. Yes.
Is exec able to change process priority?
What's the question? Can you change process priority?
Yeah.
You can change process priority. There are other system calls. Exec is not going to do that for you. There are other things you can do to change the process priority, increase it, decrease it, and so on.
Yeah, if you do it manually.
Typically, the OS handles it for you. But if you know what you're doing and you want to actually change it, you can invoke a system call from any process and cause it to change its priority. And change it from the outside, you can change it from the inside. Okay. This question is.
You said that in like creating new PCBs, there's a bit of OS overhead.
Yes.
So it seems like when you fork something, you have to create a new one, and then you have to actually call exec. Is there any way to just fork directly into what you want to execute? Or do you have to? Okay,
so question is there a way to directly execute what you want rather than doing? In the Unix world, it's a two-step process. Okay? First create, you call fork, creates a duplicate of the parent, and within the child part, you do an exec. Within the parent, you shouldn't do the exec. And that's going to be the case here because this code is going to be still the same within both. But since the parent is executing else, it's not going to hit exec at all. Okay. Now you ask the question, can you do this in one step? In Windows, where you just call create process does fork and exec in one step. So it's going to create a child process, and you specify the arguments which say this is the program to execute in the child. Okay? So Windows is slightly different from Unix. Unix is a two-step process. You have to have a fork and an exec. Okay? Yes.
Is it the same amount of overhead?
Sorry, what's the question?
Is it the same amount of
Is
overhead?
it the same amount of overhead? You have to perform the same steps. You're just splitting them into two system calls. Okay? In that case, in Windows, you have one system call. But all the underlying steps in setting up memory state, loading the file, all that is the same. And that's more than the overhead of a single system call. Okay? So there's questions on that.
What exactly is the new state of a process? Like, how is it different from ready?
Okay, what is the new state of a process? New state of a process simply says that the OS is setting up this process. Okay? It's not yet ready to run because it's maybe loading the file from disk, so you can't actually run. Set up a process, it's in the process of being set up. Meaning you created a process, but you haven't loaded all. So when it's actually ready to run, you put it in the ready state, meaning it's ready to go. Okay? Whatever you needed to do to set it up has been done. Okay? Yes,
Are the parent and child connected in a way like if the parent were for still like some reason terminate, would that terminate the child process automatically?
So question is what happens when there's always a parent-child relationship, what happens if the parent terminates, what happens to the child. So parent can terminate, right, but the child is still going to run. The child is going to be called what's an orphan process, doesn't have a parent. So by default it's going to get a parent which is the innate process, because there is no real parent anymore. Parents are not, children processes are not terminated because a parent is terminated. The processes get merged from orphan processes, become orphan processes. Okay, so this code logic is important to keep in mind. You're going to actually use it in your lab assignments and so on. So you always call fork, and this is a good skeleton to follow. Okay? Because shortly we are going to do an exercise where you are going to create not one but multiple children, and we have to see how to do this. Okay? So you call fork. After fork, always write an if-else statement where you basically say if the value returned from fork is 0, put whatever the child needs to do in the if, put whatever the parent needs to do in the else. Okay. And then you will be good. So if you follow this logic, you should actually never write incorrect code, because the fork exec you can frequently go wrong. Now let's do an exercise where you want to have this hierarchy. You want to have process A creates a child process B, the process B creates a child process C. Okay, so we want to write some code where one process creates second process creates a third process. Okay, so how do we go about writing that? I'm going to basically erase this for now. Okay, so we need to write a program that's going to do this for us. Okay, so first we are going to write this code. Okay, so you call fork, and then you write this if-else statement. Okay, now that, so you have the first process, when it hits fork, it's created process B for us. Okay. Now you want process B to start a child process, a grandchild of it. How do you do that? Yes.
Just copy all of that code inside the if statement.
Okay. Copy all of the code inside the if statement. Anyone have any other things? No, some more hands went up. So, okay. So you want the child process to create a new child. So this code should be only executed by the child and not the parent. That's important to keep in mind. So if you simply blindly put a second fork here, what's going to happen? Okay, so first A will come along, do this fork. Okay? That's going to create B. Both A and B will move on to the next line. Both of them will hit the next fork. Okay? So then what you are going to get is A is going to create another child, and B is also going to create another child. So now you are left with one more process than you want. So if you want to create two, don't just put fork right one after another. That's not going to give you what you want. What was suggested is right. You only want the child to fork a grandchild. So you basically want the second fork to be in here. Okay? So essentially you recurse. You take whatever was here and you put it there. So you are going to say j equal to fork, and then you say if j equal to 0. So this is the grandchild. And then you say else. And so this is basically B, that's C, and this is A score. Okay? Is that clear what I said? Okay. So I think what you need to expect is I give you a picture like this and say write some code to do this. So I would say now make A create 2 children. One after another. Okay? Yes, question. Go ahead.
No, I just got that.
Okay. So if you want to do this, how are you going to do that? Yes.
Just copy all the code again, anything else.
Okay, so you are going to copy all the code and put it into else. Because you want A to spawn a child, that's the first fork. Okay. And then you want A to spawn a second child, but the child shouldn't spawn any more children. So to do that, you have to now the next line fork has to go here. Okay. So you take this thing and you put it in here. And that is going to create C, but now C will be a parent of A, not the other way around. So you can, depending on what you put in if and what you put in the else, you can construct arbitrary process hierarchies.
If you want to create 2 children for A, then you put the second fork.
So you are going to put the fork, in this case you are going to put the fork here. Okay. First A created B, B gets created here. Okay. And then they both continue execution. The child B is going to start executing this, A is going to go into the else. Okay. So now you put the second fork here. Okay. Putting the second fork after the first fork, bad idea. You are going to cause bad things to happen. If you only want one of the 2 processes to do something, you want to put that either in the if part or the else part, depending on which process has to do what. Okay? Is that clear? How fork and exec work here? Okay, so I didn't say anything about exec, but then you can say B can exec Safari and C can exec Chrome and so on, and then wherever you have the child process in there, you put an exec with the right arguments and you should be good. It's exactly what we did here. Okay, so whatever one of these processes has to do, you put an exec. Okay. Last system call is called the wait system call. Here we have a flavor of wait called wait PID. Whenever you call wait and you specify a process ID, that will cause that process to block until that other process it's waiting on has terminated. In this case, the parent is waiting for the child to finish because it is calling wait PID with the child's ID. So the parent has forked the child and is simply blocked for the child to finish. Okay? Yes, Kushal.
Is the sleep call necessary?
Is the sleep call necessary? No. I ignore that for now. I just put that because sometimes it takes some time for the process to set up. So typically it's not necessary. Okay. So with this background, I'll go back one slide which I skipped, and I'm going to show you a little bit about how a shell process works. I presume all of you know what a shell is. Okay. It's a terminal that you start up and you type commands on the command line. Okay. The shell essentially is an infinite loop that is simply doing forks and execs. Okay? And you are going to write a shell in your first assignment. Basically, you have a loop where you take an input. The input is the command that the user has typed. Okay? And then you are going to, the shell is simply going to call a fork. Okay? It creates a process and take that command and give it as an exec argument to the child process. And the child process will execute whatever command you type. And then you do a wait for the child to finish. So in other words, if you actually take this code and you put it into while loop, okay, basically you are going to get a shell. Yeah, so you basically take this entire code. So each time you are going to wait for a command, wait for the user to type a command. You are going to call a fork. Say you basically type some program name. Okay, so then you are going to call fork. Within the child, you are going to do an exec. So that command starts executing, and then the shell process, which is the parent process, is going to wait for the child to finish. Once the child has finished, it's going to put out a prompt again, wait for the next command. And this is how shells work. Basically, it's an infinite loop that just sit and wait for commands and then fork off a process and execute that command within this process. Is that clear? Any questions about this? Yes?
Wouldn't the shell also get things that are not programs or not exec commands?
Yeah, so typically a shell is a more complex beast than the simple shell I showed you. Shells may have built-in commands and so on that you don't need to exec, that you can just execute differently. But for majority of the cases, whatever you type typically happens to be the name of a program. So you are going to call a fork and it will exec within that process. So that's how the default shell is going to work. There are many flavors of shell, Unix shell, there's a C shell and a bash and the Z shell and many different flavors. They all work at the same high level, but they may have small differences. Okay. So ignore things like built-in commands and things like that. We don't need exec. By and large, when you type a command on the command prompt, that's the name of a program. You're going to basically execute that. Yes.
I always thought it was a lot of fun to type in like bash inside of bash, so you can start like the bash shell.
Yes.
Instead of
You can do that.
I don't think this program would handle that very well.
No, it will do the same thing. You would have bash. So if this program is called bash, that's the parent process. You get the name of a new command. You type bash here. It's going to fork and then exec bash. And then
if you type in the name of this program.
Yeah, that's okay. You can type whatever program you want. There could be multiple instances of this is a process. Think there's a difference between a process and a program. Okay. This code, when you compile it, it's a binary. That's the program. When you start it, it's a process. So within this process, you are calling another program. You can call the same program. It doesn't matter. You will exec it and you will wait. The parent will wait for the child to finish. Okay. Yes.
So, I'm sorry for this. You said that the sleep is necessary, but when exactly?
When you need it, I won't ignore it because this was old code when machines were really, really slow. Sometimes the child process is not set up. So when you call wait and the child is not completely set up, it can give an error saying this is an erroneous process ID. So that sleep was simply there to give the OS some time to set up the child so that the process ID is a valid process ID. Most operating systems today for children very quickly, so you don't need it. Okay? But for some very old, slow systems, you may need it. Any other questions here? Okay. So now you know fork, you know exec, you know wait, you know how children and parent processes work. This is just a pictorial representation of whatever I have drawn here. So this is just showing you that that process has created a child, then the same process IDs, but then now if and an else, and then the child is going to, that's the child process has going to go into the if, the parent is going to go into the else. So this is basically just pictorially showing you that they are both the same except for CID, which is the value returned by fork, which is different in both. Okay, so we talked about fork, we talked about exec, sleep, you can ignore, we talked about wait PID. Okay, so those are the three, fork, exec, and wait are the three process management system calls. Question is?
There's a wait PID to wait for a process to execute. Is there a wait for a process to exit the new state? So instead of like a sleep one, is there?
So I think wait typically waits for the process to exit. Terminate. There is no such thing as waiting for a process to go from one state to another. There's no system call like that.
You go back to the last.
Sure. Okay.
So, are there two stacks on?
Are there two stacks? Is that your question? So when you call fork, you have two processes. They are independent processes. Each will have its own stack, each will have its own heap, each will have its own core. So there are two different processes. So yes, they will have two stacks, right? One for the parent, one for the child. Every process has its own stack and heap. So that's the child process. It has its own stack and heap. This is the parent. Yes, question.
Any
when I wait state and the process go for I/O operations which got interrupted, so will that wait will still monitoring that process to finish?
Yeah, so wait, so there are multiple, so wait in this case is overloaded term. You said IO wait, which is you're waiting for some IO to finish. There's a system call called wait, which is different from IO wait. That's waiting for a process to finish. Okay, so we are using this term wait in a somewhat overloaded way. So IO wait is a different wait. You're just, the process is waiting for some IO to finish. That's not a system call. That's just an OS operation where you've been put into the wait state. Once your IO is finished, you'll go back to the ready state. Doesn't need any system call. It's internal OS operation. This is a system call that a process invokes. Okay? So it waits for the process to finish. Okay? All right. So process termination is the last system call. I didn't actually mention this. So there are two ways to terminate a process. The process can terminate itself by calling exit. Okay? The process just finishes, that implicitly invokes exit and terminates the process. You can terminate processes from the outside using what is called the kill system call. Okay? So you can terminate them internally by themselves using exit. You want to do it from the outside, you call kill. Okay? And that will terminate the process. Yes, question there.
Can you only kill a process if it's a direct descendant of you?
Okay, can you only kill a process if there's a direct descendant of you? So when you kill a process, you have to own the process, or you have to be a super user of the system. But there is no such restriction that only a parent can kill a child process. Any process can kill any other process so long as the owner of the process is the same. If I am the user, I started all these processes, any of my processes can kill other processes. Okay? Yes.
This will go by the PID process ID.
Yes, you are going to give, I'm going to show you. Okay. So this is the GUI way of doing kill. You basically, I shouldn't kill anything important, so I'm going to kill Chrome. Right, so you just exit out. That's actually calling kill. Right, so it's going to say quit, force quit, and so on. I'm going to do a force quit, and that process is gone. Okay, that's basically internally it called kill, and it killed the process. Now let's actually kill something else. Here, so I'm going to create a dummy process. I'm going to create a process called yes. Has anybody heard of this process? Just types Y on the screen in an infinite loop. Okay. Why it exists, I don't know, but it is the. So it is running. So I'm going to actually look for it, and so it has what's the process ID? I think it's 50 something. Okay, so it is one of these. So I'm going to do kill -9 50546. Okay, that's yes running, and I think that's the process ID. We'll find out if that's the process ID. Then I kill something else. Okay, so I killed it. So I do kill -9. You see that the process has been terminated. Okay, so that's just that kill command is just calling the kill system call. It took a process ID and it terminated the process from the outside. Okay. You can write code that does the same thing. You can take the process ID and call the kill system call. That's what the kill program has done. Okay. So this demonstrated to you that the first shell was not the parent of the yes process, because I had a second shell that at the started yes, but we could kill it in any case because they both had the same level of privileges. Okay, so you don't have to be a parent process to terminate another process. You just need the right privileges to do this. Okay, so this is the code to do process termination, which is we're going to do a for. Okay. Within the for, you have a child process is not doing anything, it's just sleeping for a few seconds. Okay. And then if you haven't killed it by then it's going to exit, and here you have a parent. You basically say type any character. The child will type something, and then it's going to go and kill the child. Okay. There's some simple sample code that forks a child. Here the parent is the one that is terminating the child process. Okay. Yes, question. So question is, what does kill return? So depending on whether the kill was successful or not, you may get a valid code saying yes, it worked or it didn't work. So in particular, here the child process is going to sleep for 5 seconds and enter exit. Right? So if you and here you're waiting for input before you proceed. So if you wait for more than 5 seconds, the child is already gone. So the skill will give a process ID that no longer exists on the system. It will return an error in this case. Okay? Which is why you're checking whether you get a valid return value or an error. Okay, so basically each of the system calls have return values that tell you what happened. Was it successful? Did it give an error or so? So if the process doesn't exist, you'll get an error value. In this case, you will not say failed to check. But in most cases, if you do it at the right time, you will be able to kill the child process. Does that answer your question?
Well, that's only gonna the connect of the tab is only gonna run if kill doesn't return.
So I don't remember what. So you're asking what's the return value? We need to look at the man page. I believe that if it's 0, that means it killed it. If it's negative, that it means it did not kill.
Okay.
That's my recollection of what it was. So that's why it says not kill. Any other questions here? Okay, so you will write some code to also terminate processes and try out kill. Okay, and then you will figure out how to create processes and terminate processes, start other processes, and so on. Okay, so all that is coming in lab 1 soon. Okay, so we will move on, talk a little bit about a few minutes left, talk about cooperating processes and see how to do message passing and things like that. So we talked about process management, which is creating processes, managing children processes, terminating, and so on. Now we will see how processes communicate with one another. So you may have two processes. Any two processes in the system are independent if they have nothing to do with one another, but if they communicate with one another in any way, they're called cooperating processes. Cooperating processes are processes that communicate, okay, for whatever reason. Why they communicate is orthogonal here, but they communicate. So any two processes in the system are either independent or cooperating. Okay? Now if you have cooperating processes, question is how do they communicate with one another? They need a way to do this, and we'll look at some sample code and we'll look at some system calls that allows us to do this. Okay? So this sample code is referred to as producers and consumers. We are going to come back to do producers and consumers when we do synchronization. I don't know if you did some of this in 230, I presume you encountered producers, consumers at that point in time. We will come back to it, but here's just an example of two processes. One is a producer, one is a consumer. Producer, as the name suggests, is a process that just creates data items, okay? And it sticks it into a buffer. So it sits in an infinite loop and it basically creates a data item, puts it into a buffer. Okay? It's a circular buffer. So if the buffer fills up, the producer has to actually wait. Okay? Otherwise, it's going to start overwriting data items. Okay? Consumer is another process that consumes data items that the producer has produced. Okay? So it's also sitting in an infinite loop. And it's simply pulling, there's this indentation problem here, this next should have been indented. So it is just simply pulling data items from the shared buffer. But this buffer is an array that's shared between the two processes. Okay? So you're going to stick value into the data buffer, and the process is pulling value from the buffer. Okay? So the picture to keep in mind is this one. So you have producer, you have a buffer here. You have a consumer. So your producer is putting the values into the data buffer, consumer is putting values from the buffer. Okay, and they are both in an infinite loop doing this repeatedly. Okay. So the reason I brought up producers and consumers is this is a form of communication between the processes. Okay. This is what is called implicit communication, unstructured communication. Because by sharing data between two processes, that's a form of communication. And the data item could be anything that allows the producer to communicate with the consumer. So shared buffers between producers and consumer is a form of communication. So, and this form of communication uses what is called shared memory. This buffer is a shared memory region between a producer and consumer. Because if you remember what I told you 2 classes ago, I said one process can never access the memory that belongs to another process. for protection reason. Otherwise, you can go and overwrite. Okay? Now, I just told you that producer is producing something, is putting it into a buffer, consumer is pulling something from the buffer. Okay, so that should have told you that this is something unusual, because ideally, if the buffer is an array that belongs to the producer, the consumer has no access to it, because that's memory that belongs to the producer, or vice versa. Okay? So for this to actually happen, this data structure has to be in a special memory region called shared memory that's explicitly allocated for two processes to share. Because by default, any memory that belongs to one process is inaccessible to any other processes. Okay? So this is going to require us to implement some system calls to implement the shared memory region. Okay? So that's the reason I brought this up. So if you really want producers and consumers to be two separate processes that communicate, that buffer has to be in a shared memory region. Okay? And I'm going to the other way to do this is to actually use what is called explicit message passing. Okay? That's the code shown here. Rather than using a shared buffer, you are simply going to send messages. So your producer is going to produce a data item. It's going to use a special system called send, which allows you to send anything in a message. So you take the data item, you put it into the send system call, you specify the process ID of the consumer, and you just say send. Okay? On the other side, you are going to do receive. Okay? You are going to receive whatever messages are sent by the consumer. So now you are in an infinite loop. You are explicitly sending messages. You are communicating using message passing. Okay? That's the second form of communication. You can either use shared memory or you can use message passing. Okay? Message passing can also work across machines. Here, these two processes are on the same machine, but the consumer could reside on a second machine. In that case, you are also going to use message passing. You use special kinds of messages that use TCP/IP abstractions called sockets, because you have to communicate over a network for that message passing to succeed. But here, let's assume that both producers and consumers are on the same machine. So you can use a system call to send and receive messages. You don't need to communicate over a network. The messages are inside a single machine. And they are passed between processes inside a machine. Question?
So, since using system calls, does that make this method less efficient than the other one?
Using system call, does it make this method less efficient than the other one? The shared memory is somewhat more efficient because you have to use a system call only to allocate this region the first time. And since after that it's a piece of memory that's accessible to both. So it's simply reading and writing memory, which is clearly more efficient than invoking system call. So you are right in that sending and receiving messages are repeated system call. They will incur higher overhead than simply allocating that shared memory region once and then doing this repeatedly. Okay, so one last piece of code before I end. So the mmap system call is a special system call that allows you to create a shared memory region. There are other system calls that also allow you to do that. Mmap stands for memory mapping. Okay? And you'll see that there are some arguments to mmap that we have passed. In particular, we have said allocate a region of memory, make it writable. That's an argument that says prod underscore write. And then you also have an argument that says make it shared. Okay? That makes that region of memory shared between multiple processes. Okay? So you have to invoke that system call in order for that buffer to be accessible to, if you call it in the producer, you make it accessible to the consumer and vice versa. Okay? And so once you do that, then it's simply a matter of writing to this array. The array just happens to be in the special region of memory. But it looks like a standard array from the programmer's perspective. It just sits in a shared memory region rather than in regular memory of that process. This question.
I don't recall using mmap when in deep learning. Can you just use the static keyword?
Static keyword.
In C.
So presumably you did producers and consumers using threading, not processes. Is that true, or do you do processes?
We use threading.
So we will come back to threads. If you are using threads, the threads reside within a process. You don't have the memory of the process is shared across threads. You don't have to do any of this. We are talking about independent processes, not threads. Big difference between the two. Okay, so code works differently if you have threads that are producers or consumers, or if you have processes that are consumers or producers. Okay. So these are independent processes, so you have to do extra work. Okay. So you will have to invoke system calls and things like that. Okay. So we will end it here today, and I'll continue with this tomorrow. Okay, in the discussion.